Okay, can everybody hear me? Okay, then I will start my talk. Okay, hello everyone, my name is Chung-En Tsai, and today I will talk about learning content states with the log loss. And I'm an undergraduate student from National Taiwan University. Okay, and then this will be today's outline. So we will first introduce the problem formulation, and then we will see some recent progress on this problem. And then if time permits, we'll present following the regularized leader approach. And then at last, we'll discuss some open problems on this topic. And if you have any problem during the talk, feel free to interrupt me. Okay, and so let's, before we introduce the problem, since we are talking about quantum states, so we need some mathematical formulation of a quantum state. So here's a one-page preliminaries. Okay, and so first, we need to know how to describe a quantum state. What is the mathematical formulation of a quantum state? And in quantum mechanics, a quantum state is represented by a so-called density matrix. And it is a complex D by D matrix that is Hermitian, positive semi-definite, and with trace equals to 1. Okay, and this is the definitions of a density matrix. And in real world, if you have a q-qubit quantum system, then the dimension to describe this quantum state, you need dimension equals to 2 to the q. It's the exponential. And the density matrix can be seen as a quantum generalization of the probability simplex. That is the set of vector, d-dimensional vector that have non-negative entries and sums to 1. So you can see that the definition of the positive semi-definiteness corresponds to the non-negativeness, and the trace 1 condition corresponds to the summation to the 1's condition in the probability simplex. Okay, and since we are consider some optimization problem, learning problem, and we usually need a vector space. And for example, for the probability simplex, we may need the RD to consider it in a bigger vector space. So here for the density matrix, we consider the vector space as the D by D Hermitian matrix. And to define gradients Hessian, we may need the inner product. And on this set, the inner product is defined as like this, which is called the Hilbert-Schmidt inner product, which is the trace of the product of 2 Hermitian matrices. Okay, so we can see the set of Hermitian matrices as a quantum generalization of the Euclidean space. And for this notation, this represents, since we'll use it later. So this is the set of Hermitian positive semi-definite matrix. Okay, so it can be seen as the quantum generalization of the non-negative orthant. And at last, the last thing to introduce is the, since we are consider learning a quantum state, so we need to have some method to obtain information from a content state. In physics, this to obtain information from a content state, we do a measurement on the content state. So suppose we have a content state rho represented by a density matrix, and then we measure it by some device, and then the content state will change to another content state, and then we'll obtain a measurement outcome, C. And let's talk about how to make the device here. So this device is called a positive operator valued measure, a POVM, and it is a set of Hermitian positive semi-definite matrices that sums to the identity matrix. And this is the definition. And if we measure a content state rho by a POVM, then we'll obtain a measurement outcome, C, which is a random variable. Taken values in 1 to the n. This n corresponds to the how many matrices is in the POVM. And the probability of C equals K is the inner product. Here, I omit the HS subscript. It's the inner product between the case matrix and the content state rho. Okay, this I will not explain why this is, just think about as an axiom of how a measurement work. So, okay, so this is the preliminary part, some notations. Okay, then now we'll, okay.
I'm wondering, so here you define the inner product as the trace of the product of sigma and the rho, right?
Yes.
But here I'm just wondering, because for inner product we need it is required to satisfy the conjugate symmetric property. So in that case, is it still the inner product is defined as the trace of the sigma times rho, or something like sigma times the rho formulation?
Since we are talking about we see the set of Hermitian matrices as a real vector space. So in general, for general complex matrices, the inner product will define as what you have said. That's something like this. But for our case, because the metric is Hermitian, so the conjugate of the Hermitian of sigma equals itself.
Okay, so if that is the case, because here you say that h to the d power is you consider a subset of matrices which are like in the C to the D times D, right?
Yes.
But if you restrict yourself to only symmetric matrices in the real space, then why not you just restrict your domain to like x to the d equals to like all the matrices in the R D times D, or in the symmetric?
Since to describe a content state, we need a complex matrix. So sorry, can you I do not understand your questions. Can you?
So my question is that because if you are considering about like complex matrices, then in that case, to preserve the conjugate symmetry of inner products, it'll be more reasonable to define the inner product as what you have just written, namely the trace of something like a sigma. I guess it is like sigma times rho Hermitian, something like that. But here you define the inner product as the trace of sigma times rho. So in
Yes.
that case, if you are considering the complex matrices as you have done here, I'm wondering if such definition still preserves the conjugate symmetry of which is something an inner product should behave.
Sorry, I forgot what the conjugate symmetry. What is the definition of the conjugate symmetry? I forget about this.
Okay, it means that suppose you times rho by some complex number lambda, right?
Yes.
Then in that case, the result will be the original result times lambda, the conjugate of the lambda.
Something like this.
Yes.
So in our case, since we see the complex matrix as the Hermitian matrices as a real vector space, so in fact we will not multiply rho by a complex number. So in this case, lambda and lambda conjugate will be the same.
Okay, I see. Because you're considering Hermitian matrix. Okay, I'm fine.
Okay,
yeah,
okay.
That's fine. Okay, thank you.
Okay, thank you. Okay, then we'll talk about the problem formulation of learning content states with the log loss. So this is the problem. So it is an online convex optimization problem. And so it is a multi-round game between the physicist and the reality. And there is a round index T. So at the T's round, the physicist will first chooses a quantum state rho T in the set of density matrix. And after seeing what physicists choose, the reality will adversarially chooses a Hermitian positive semi-definite matrix and define the loss functions to be the minus log of the inner product between AT and rho. And then after the reality chooses this Hermitian matrix, the physicist will suffer a loss FT of rho T. Okay, this is the formulation of the game. And the physicist's goal is to make a quantity RT to be small in T, where RT is called the regret of the physicist. And it is defined as the maximum of RT of rho, where rho will taken, the maximum will taken over all the density matrix. And RT rho is defined as the cumulative loss of the physicist. Cumulative loss of the physicist minus the cumulative loss of the comparator rho. And I will not talk too much about the definition of the regret. And if you are interested in why we are defining such measurement, and you can check some online learning books. Okay, so the things to remember is that it is a multi-round game, and the loss function has this form, where AT is a Hermitian positive semi-definite matrix. And our goal is to make this quantity as small as possible. That is the cumulative loss of our algorithm minus the cumulative loss of a fixed competitor. Okay, so then I will introduce some interpretation of this problem, why the problem has this loss function. And why is this problem meaningful and important? Okay, so let's consider a statistical problem called quantum state tomography. So this is important in designing robust quantum devices. So if we want to build a quantum device, when building it, we may want to know what a quantum state is in our device, but we cannot observe the quantum state directly. So we need to perform some measurement and then recover the quantum state from, not recover, maybe estimate the quantum state from our measurement outcomes. So the problem is like this. Suppose we have an unknown quantum state rho natural in our device. Then what we want to do is to estimate rho natural, to understand what rho natural is, but we cannot directly observe it. So what we do is to first we copy rho natural to capital N copies. Okay, assume this can be done. And then we use capital N many POVM to measure it. So we measure the first copy by E1, and then the capital N's copy by En. And then, as we have said before, after, for example, the first copy, after we measure it, the quantum state will collapse to another quantum state, and then we'll obtain a measurement outcome K1 with probability. Suppose the realization is K1. Then we know that the probability of observing K1 is the inner product between the K1's matrices in E1, between the A1, K1, and the unknown quantum state. And this is similar for other measurement. So for example, the last copy, suppose we get the outcome is Kn, then the probability of observing Kn is the inner product between An, Kn, and the unknown quantum state. So what we want to do is to, after observing K1 to Kn, and to know what rho natural is. And there is a very natural approach. So I forgot to mention one important assumption, that there is one assumption that is important, that the measurement are independent. The measurement outcome are independent. Okay, this is important assumptions to make the following approach reasonable. So suppose the outcome is independent, then a natural approach is to consider the maximum likelihood estimation. So so after we observe K1 to Kn, we know that the probability that we observe it is the product of those probability because of independence. So this is the probability that we observe the outcome K1 to the Kn. Then we construct an estimator rho hat by maximize this probability. So we remove this natural sign, and then we want to maximize this. We want to find the rho that maximize this probability. And then, so this is equivalent to finding the minimizer of this convex optimization problem. by taking minus log, you will turn the product into the summation, and then the maximum into minimum. Therefore, the maximum likelihood estimator is given by the minimizer of this problem. And what we hope is that this estimator is when the measurement are performed many times, then the estimator is close to the unknown quantum state. Okay, and you can see that this is very similar to the cumulative loss of the learning quantum state problem. Okay, and in fact, this is the previous problem is motivated by this statistical problem. And but this convex optimization problem, you can solve it by Newton's method, and it will provably converge. So, in fact, we can solve these problems. So, why do we consider the online version of this problem? The online, let me call this MLQST. So why do we want to consider the online version of MLQST? This is because there are two reasons. The first reason is that it can be proved that okay, so if we can solve this problem and obtain an estimation of the unknown quantum state, and our arrow can be decomposed into two parts. The first part is the statistical arrow, and the second part is optimization arrow. The optimization arrow part is corresponds to how accurate we solve this problem. So there is an optimization arrow. As for the statistical arrow, this is because that the data we observed, the outcome we observed is random. So it is possible that we are very unlucky, and the data is very biased, or it is very bad. So by the law of large numbers, or central limit theorem, we need n large so that the statistical error is small. However, it was proved that to make your statistical error small enough, the n needs to be as large as big omega in 2 to the q. So where q is the number of qubits in your quantum device, so this is omega d. So this means that in this problem, in real world application, the capital N will be, the sample size will be very, very large, since it grows exponentially with how many qubits your quantum device have. Then if you want to apply Newton method to solve this problem, it will be very inefficient because you need to compute the Hessian, and which will takes maybe 2q to the 3, since you need to compute matrix inversion. And this will make computation very inefficient, and maybe your memory is not enough to do such computation. And therefore, what we want to do will be design some stochastic algorithm that is at every iteration, we randomly sample one n, and then use this use only one segment to do optimization. And one approach to design such stochastic algorithms is to consider the online version of this problem. So, and then you can use a technique called online to batch to transform an online algorithms to a stochastic algorithm that provably converge. Therefore, this is one motivation why we considered the online version of it is to design stochastic algorithms for solving the MLQST problem. And the second motivation to consider the online version of it is to, since we have assumed the measurements are performed independently. However, this assumption is maybe unverifiable or unreal or even unrealistic because when we physically implement such devices, there may be some correlations, and it is not possible to do the measurement independently. Therefore, such assumption, the independent assumption may be unrealistic. So such statistical problem may be not good for such learning problem. And consider the online learning problem that do not assume any probability distribution behind AN may be more suitable. Okay, this is an application of the learning content states with the log loss problem. And why the loss function looks like this? This is because, in fact, this is the product of the probability, and we take the minus log. And yes, this is okay. And then the third interpretation is helpful for designing algorithms. So the learning content state with the log loss. So it can be seen as a content generalization of the classical online portfolio selection problem. So this is also an online convex optimization problem, and it is also a multi-round game between the investor and the market. So similar to the problem we have described before, the investor will choose a distribution xt in the probability simplex, and this corresponds to the density matrix in our problem. And the market will adversarially chooses a non-negative vector AT and define a loss minus log of the inner product between AT and X. And this just corresponds to the capital AT Hermitian matrices. And this loss corresponds to the R loss, which has the same form. So the learning content states problem can be seen as a content generalization of the OPS problem. And OPS has received many attention these years. And so since it is a content generalization, so if we have an algorithm for the OPS problem, then we can do a content generalization to the learning content states with the log loss. Okay, are there any problems? Then I will go to the next page. Okay, so now we describe why the problem we have discussed why the problem is important, and then we'll now discuss why the problem is hard. Okay, so first, for the regret, we want to make the regret as small as possible. And for the regret part, you can notice that the loss function is neither Lipschitz nor strongly convex, which violates the standard assumption in online convex optimization. So this is the form of the loss function that the reality will choose each round. And you can take the gradient of it, since, okay, you can take the gradient has this, this form. And the loss function is not Lipschitz because AT is only required to be positive semi-definite. So this inner product can be as small as possible. Therefore, the gradient can be as large as possible. So it is not Lipschitz on the set of density matrix. And it is not strongly convex because, so if we look at its Hessian, it is strongly convex if there exists a positive mu such that the Hessian is lower bounded by mu times the identity matrix. But this, we cannot choose this such mu because, for example, if you choose AT to be 1, 0, 0, 0, it is a Hermitian positive semi-definite matrix. And then the numerator is the square of the AT. And then it still equals to this. Then it is impossible to find a positive mu such that this inequality holds. In this case, mu must be 0. Therefore, FT is not strongly convex. So since it violates the standard assumption in online convex optimization, so further new algorithms must be designed. And beside regret, we also care about the efficiency of our algorithm. And we have said before that the dimension D is exponential in the number of qubits. So if we want to compute the so it is acceptable to design some algorithm that's with maybe D square per iteration time complexity or D to the 3. But if you have some algorithm that D to the 6 per iteration time complexity, then this will be too high and hard to implement in practice. Okay, so these are the two hard parts of learning quantum state with the log loss problem. And before we move on the recent progress of this problem, let's talk about a related problem that you may see in the literatures. So this is the problem called learning quantum state with, it is a problem also called online learning of quantum states. And I add this with Lipschitz loss because the proposed problem or the proposed algorithm only works for the Lipschitz loss case. So it is a similar problem that it is an online convex optimization problem, and the physics also chooses a quantum state rho T. But for the reality, it chooses a Hermitian positive definite matrix as well, but the loss function is not minus log of the inner product. Instead, it has this form where we can choose LT. And the LT is required to be a Lipschitz loss function. Therefore, you can check that this FT it's Lipschitz. And it falls into the standard online convex optimization problem. So there are many algorithms to solve this problem. And some example of LT, let me remove this example. Okay, so an example of LT is the L1 loss. So if we use this LT, then this loss function is something like this. And this is a problem of, and you can, this inner product can be interpreted as the expected outcome. So why is it the expected outcome? So the expected outcome is this corresponds to 0 and this corresponds to 1. So the expected outcome is 0 times the probability of observing 0 plus 1 times the probability of observing 1. So this value is the expected outcome. And as for BT, you can think it as some true answer. So the true expected outcome is BT, although there is no true answer in this problem. And then this loss function measures how our predicted expected outcome differs from the true expected outcome. Okay, so but our algorithm, our problem are different to this one, since the LT we choose is the negative logarithm, and the negative log is not a Lipschitz function, so the algorithm they propose does not apply to our problem. Okay, so in the next slides we will see some algorithms that are applicable to learning quantum states with the log loss. So are there any problems? Okay, so let's see. There are as far as we know, there are 4 algorithms that are applicable to learning quantum state with the log loss. And the first 3 algorithms that both enjoys the square root of dt regret, and the per iteration time complexity is d to the 3. And the first algorithm is introduced by Nestrov in 2011, although I think he are not aware of this problem. So, and he named the algorithm the barrier subgradient method. And if you check its form, it is in fact the one log barrier following the regularized leader algorithms. It is the following the regularized leader algorithm with log barrier regularizer. And then there are 2 algorithms that are designed by our lab. The first is the quantum generalization of solve base for online portfolio selection problems. This is a quantum generalization. And then the other called log barrier online mirror descent is also a quantum generalization of the same algorithm for online portfolio selection problem. And the fourth algorithm called Schrodinger's Bisons, and it is also a quantum generalization of an algorithm called Bisons for online portfolio selection. And it enjoys the logarithmic regret. So for the regret, Python is significantly better than the above three algorithms. However, its per iteration time complexity is d to the 6, which makes the implementation very inefficient, since it needs to compute some Newton steps in its iterations. And you can see that both the last three algorithms are very new, and it is in 2020, 2022, 2022. And here's an upper problem. That's what is the optimal regret for this problem. So this is currently unknown. But for online profiler selection, the optimal regret is d log in t. So what is the optimal regret? Is it also d log t? Or it is d square log t? Or maybe there are other possibilities. Okay, then in the later we'll focus on the first log barrier following the regularized leader approach, but with analysis different from the original analysis by Nestrov. Since yes. Okay, so let's see one approach to solve the problem. Okay. So let's recall the FTRL algorithms. Okay, so this is the algorithms. FTRL with linearized losses. So the algorithms iterate as follows. So we need to pick a regularizer H and the learning rate eta positive. And then for the first step, the physicist does not know any information. So it chooses row 1 to be the minimizer of H. And then for the following iterates, for this is a notation that we define gradient t to be the gradient of ft at row t. And we choose row t plus 1s to be the minimizer over the density matrix. And the objective function is the summation of the inner product between the gradient and row and plus a regularizer. And for the first part, this corresponds to the linearization of the loss function. So we have, so we have this first order approximation. This is tau. Okay, so this is constant, so it does not affect the minimizer's position. So we do not write this, and we do not also write this. So this corresponds to the first order approximation of the loss function. And we add a regularizer to make the iterate stable. And this is the textbook result. So if we take the regularizer to be the two normal, let me see. So what we need to take here is something like, I write this, it's a classical case. So for the quantum case, it should be, so something like the two norm in the classical case. This is called the Shetton two norm. or let me write this as the trace of rho square. Yes, and then then the regret will be upper bounded by h rho minus the mean h rho 1 over eta plus 2 over eta and times the summation of the this should okay the dual norm square of the gradient. And since we have this regret bound, so we may need to assume that this term is bounded. So then we may obtain a meaningful bound. So if we assume that FT is Lipschitz with respect to this norm. So suppose we have it is Lipschitz means that its gradient is bounded. So suppose we have this, and then this regret bound will can be upper bounded by this. Can be upper bounded by this. And suppose this term is also bounded, then we can choose eta to be we can choose eta to be like this. And then the regret will be square root in t. The regret will be square root in t. And we however, for our loss functions, we have seen before that FT is not the gradient of FT is unbounded. Therefore, it is not Lipschitz with respect to any fixed norm. So this textbook results thus cannot be applied. So we may think reversely that we may think reversely that if FT is Lipschitz with respect to the true norm, then we choose H rho to be this, and then we have a meaningful regret bound. So so what we want to do is that if we can choose some norm such that FT is Lipschitz, then we can find some H. This I'm not saying properly. So so since FT is not Lipschitz with respect to any norm, so there is a clever idea that suppose we can find some position varying norm. So I'll say position dependent norm. Let me erase this. So suppose there's a clever idea that suppose if FT is Lipschitz with respect to some position dependent norm. Say so what is position dependent means? It just means that there is a norm that depends on the position row. So suppose we can, and this means that it is Lipschitz with respect to this norm means that suppose the gradient of f at row t measured in the norm at row t is upper bounded. Then if we can find such position dependent norm and we find some H that's similar to the norm, then we may obtain a regret bound like this, but replace this norm by the position dependent norm. this is the idea. So since FD is not Lipschitz with respect to any fixed norm, so we may try to find a position-dependent norm such that FT is Lipschitz with respect to the norm, and to derive a regret bound associated with the norm. Okay, so let's see the precise statement. So this is the key observations. Okay, so the position-dependent norm we choose is defined as follows. So we let H rho to be the minus log determinant, which is the logarithmic barrier, which we'll call it the logarithmic barrier. And then we define a norm, define a position dependent norm like this. So at the position rho, the norm is defined as the second order Fraser derivative of H at rho in the direction sigma and sigma. And you can write this down and it will be this. The trace of the square of the product of rho inverse and sigma. And this norm will be called the local norm associated with the function H. And we can define its dual norm like this. And it can be, you can derive that the dual norm has a closed form like this. And we'll call this the dual local norm. And the key observation is that for our loss functions, so it has the form like this, the minus log of the inner product between A and rho. Then the gradient of F at rho measured in the dual local norm at rho is uniformly bounded. So this is the key observations. So we can find, and for the following, we want to derive a regret bound based on this norm. And what H should we choose? Then the most natural H to choose, the regularizer H is to choose this. Okay, so let's see the resulting algorithms. So this is the following the regularized leader with the logarithmic barrier. So we pick H rho to be the minus log determinant rho, and the learning rate positive eta. Then we choose rho 1 to be the minimizer of H, and the notation is the same. And at the t+1 iteration, we choose rho t+1 to be the minimizer of the summation of the linear function plus the regularizer. And it can be proved that, and we will later present that the regret of the above algorithm is upper bounded by d times log t over eta plus, this corresponds to this roughly speaking corresponds to the term H rho minus H rho 1 over eta. And plus the second term in the regret bound is eta t over 2 times 1 minus eta. And this corresponds to the summation of the regret of the norm of the gradient. And there is some technical issue, so there is an additional 2 here. And it can, the per iteration time complexity of the above algorithm is d to the 3. And the bottleneck is that we need to compute an eigenvalue decomposition. And if you are interested in the implementation, you can see the following papers. Okay, so there are so let's see the proof of theorem 1. That how do we make the regret bound of the following the regularized leader to make this term measured in the local norm instead of a fixed norm. Okay, so the proof of theorem 1 consists of 2 steps. The first step is a decomposition lemma. So what we want to bound is the regret of rho, and by definition, it is the cumulative loss of our algorithm minus the cumulative loss of the competitor rho. And by convexity, it can be upper bounded by the inner product between the gradient at rho t of gradient of ft at rho t and the rho t minus rho. And the following is an equality. So you can check it yourself that this summation can be decomposed into the following 3 terms. The first term is we are familiar with the first term. That is h rho minus h rho 1 over eta. So we leave this term. And for the second term, it is the summation of ft plus 1 at rho t minus ft plus 1 at rho t plus 1. So you can see this as the difference between rho t and rho t plus 1. So if rho t and rho t plus 1 are close, then this value is small. So it characterizes how stable our iterates is. And the third term is ft plus 1 rho t plus 1 minus ft plus 1 rho. And since rho t plus 1, maybe I forgot to introduce the notation ft plus 1. So ft plus 1 is this. It's a summation of the linear function plus the regularizer. And rho t plus 1 is the minimizer of ft plus 1. Therefore, for the third term, since rho t plus 1 is the minimizer of ft plus 1, so this term is non-positive. Therefore, we can simply ignore this. So what we need to do is to upper bound this, which characterize the stability of our iterates. And what we'll prove will be this. So this this difference is upper bounded by eta times the gradient, the norm of the gradient square over 2 times this. And you can see that this function, as a function of this, is an increasing function. So, and we also know that this term is upper bounded by 1. So it is upper bounded by if we plug 1 into here. So it is upper bounded by eta over 2 times 1 minus eta. Okay. So what we need to prove is only lemma 3. Okay, so first, why do we expect that lemma 3 is correct? So what we want is to show that from lemma 3 is something like that. So if eta is small, it says that if eta is small, so if the learning rate is small, then rho t and rho t plus 1 is close to each other. Right. Okay, so what lemma 3 says is like this. If eta is small, then rho t and rho t plus 1 are close to each other. So why should this be true? Okay, so let's see the iterates. So the following the regularized leader looks like this. So rho t plus 1 is the minimizer of the linear function plus the regularizer. So if eta is small, then this term is very large. So this term is very large, so this term dominates, and which will make this the first term negligible. And therefore, rho t and rho t plus 1s will look similar. An important property is that h is curved. So if h is linear function, then the argument what I said before does not hold. It's not true. So this is the graph of the minus log x, which is the classical logarithmic barrier. And you can see that it is curved. Therefore, if you times a very large constant, if eta is small, and then the constant will be very large, so which will make the iterates stable, because this part dominates and this part is something like this, or if eta is larger, then it will like this. Okay, so we will make this part more rigorous. So, and we need to introduce some definitions. So a convex function phi is said to be self-concordant if the third derivative is upper bounded by its second derivative. And one fact is that h is self-concordant. So h is the minus log determinant h. Determinant rho. And it is a standard example of a self-concordant functions. So you can check Nestrov's books for references. So h is a self-concordant functions. And since eta times ft is linear functions plus h, so eta ft is also self-concordant. And for self-concordant functions, we have the following inequality. So phi y is lower bounded by its linear approximations plus an additional term. And how to interpret these inequalities? So it looks like strong convexity. So if your omega if this term is replaced by this, then it is the definition of strong convexity. But now this is not a strongly convex function, and instead this term is replaced by this term, where omega is t minus log of 1 minus t. So this characterizes how curved the function phi is, for how curved the self-concordant function phi is. And so we can see the proof of the stability lemma. So since eta times ft plus 1 is self-concordant, it has such a lower bound. So if we plug y to be rho t plus 1, x to be rho t, and then you move the inequality, rearrange the inequality, then you will get the blue inequality like this. This use the self-concordance of h of eta times ft plus 1. And then we want to use the iteration rule of rho of the following the regularized leader. So we decompose this term, we decompose the gradient into two terms, the gradient of ft at rho t and gradient t. And then we can upper bound this by the optimality condition of the iteration rule. So since rho t is the minimizer of ft, then this inner product will be upper bounded by 0. And for the second term, we use Holder's inequalities to upper bound it by the norm of the gradient times the norm of rho t minus rho t plus 1. And this term remains the same. And then at last, we use the so-called Fenshaw-Young's inequalities. So this is the convex conjugate of omega. So it is defined as this. And from the definition, it is the, so if we think this as T, this as S, this as T, then, and let S to, then this will be upper bounded by the definition of omega star, since this value is the supremum of ST minus omega T, and ST minus omega T will be upper bounded by the convex conjugate of omega. And at last, we just divide both sides by eta. Then we obtain this difference is upper bounded by eta over the convex conjugate of omega at eta times the gradient norm over eta. And since the convex conjugate of omega is, you can solve it and it has the closed form, and it can be upper bounded by s squared over 2 times 1 minus s. So by this inequality, you can obtain this. And since the function is increasing, so you can upper bound it by this, and the proof will come. And the proof is complete. Okay, so this will be the analysis of the log barrier following the regularized leader. And there will be no proof. Okay, so this is some experiments. So we have said that we can turn an online algorithms into a stochastic algorithm for MLQST. So we can turn it for MLQST. So this is the numerical experiments. So we consider the LB-OMD algorithms, and it has similar time complexity to LB-FTRL. And the QSOF-based algorithms we have discussed, we have mentioned before. And there are two. These two are stochastic algorithms, and these two are batch algorithms. And Aurora is used in practice. And you can see that the setting is that we want to estimate an unknown rank 1 quantum states of 6 qubits. And the dimension is 2 to the 6. So it's a 64. And the data size is 400,000. And this is the experiment results, so that we can see that the two stochastic algorithm is, although it has their, it does not converge quite fast. So compared to the two batch algorithms. So there are still some improvements for designing stochastic algorithms for MLQST. So there are 3 important open problems for learning quantum state with the log loss. So the first one is what is the optimal regret for learning quantum states with the log loss. And this we have mentioned before that for OPS, the regret is d log t. The optimal regret is d log t. And what is the optimal regret is a fundamental problem. And the second open problem is to design design optimal algorithms that attain the optimal regret. So for OPS, this is the universal portfolio selection by cover. It has regret d log t. So is it possible to generalize these algorithms to learning quantum state with the log loss? So this is another important problem. And the third open problem is to design a square root dt, to design algorithm that achieves square root dt regret with only d square per iteration time complexity. This is the best possible complexity because to construct a density matrix, the density matrix has already d square entries. So we do not expect that we can design an algorithm that is faster than d squared. And some possible direction is to design projection-free algorithms. Since, yes, the projection-free algorithms. And if you are interested in any of these open problems and you want someone to discuss, and feel free to email us. Okay, so there are 3 conclusions. So learning quantum state with the log loss is an online convex optimization problem and its application, including designing robust quantum devices by solving the MLQST problems. And the second conclusion is about the analysis of following the regularized leader. And that some problems you may see, the gradient may seem unbounded at first, but it may be bounded under some suitable position-dependent norm. And the third conclusion is that designing computationally efficient algorithm is an important and challenging research directions. Okay, so the talk is my talk is complete. So are there any questions?
Okay, thank you. Is there any questions? Okay. If there is no other question, then thank you for Mr. Tsai for his presentation. I think it's very interesting to combine these 2 fields, the optimization, practice optimization technique to solve the physics in quantum physics problem. Okay, thank you for your presentation and see you next time. Goodbye.
Okay, thank you. Goodbye.